These videos are offered on a pay-what-you-like basis. You can pay for the use of the videos at my website. There's a link to my website in the info box. The address is www.freelance-teacher.com/videos.htm, or you can just use the link in the info box. Thank you. The way you're likely to see this tested on the exam is in terms of a pressure volume curve. And you know that the exam problems like to be multi-step. So they'll probably give you a bunch of different processes, isothermic and adiabatic and constant volume and whatever. And you have to figure out one small thing from each step and then try to put that information together. So one of the main things that other video series went through is it just went through the various basic types of processes. So we can review that, especially because there was a couple of equations that I didn't have time to go over in that introduction. So we can go over some of the more advanced equations that you probably would need on the test.
Okay.
Let's start with a constant pressure case. There's a special name for some of these processes. I don't know if you happen to remember what the name for constant pressure is.
Yeah, it's like isobaric.
Good.
Isobaric. Yeah.
Like a barometer.
Yeah.
A barometer is used for measuring pressure, so this is constant pressure. Iso means same or constant. That's a term you might be expecting to know. So what would the PV curve look like for an isobaric process?
It's a horizontal line.
That's right, not just a line, but a horizontal line. Good. Because that's what it means for the pressure to be constant. Now, how would we calculate the work that was done by an isobaric process?
It's the area under the curve.
That's right. So we know in general that the work is the area under a PV curve. And this is a particularly easy area to find. How would you calculate this area?
You would just multiply the change in volume times the pressure.
Right. Since this is a rectangle, we can just do length times width. So it would be the change in the volume times the pressure. There's no distinction here between the initial pressure and the final pressure since the pressure is constant. So it would be P delta V. Now, one thing that you have to always watch for is whether you're focusing on the work done by the gas or the work done on the gas. So would this give us the work done by the gas or the work done on the gas?
If it's positive, it's the work done on the gas. If it's negative, it's the work done by the gas, I think.
I think you're thinking of the right idea. However, so let's see. So let's say that the volume is increasing. In that case, would the gas be doing work or would work be being done on it?
The gas is doing work.
Right. In this case, work would be done by the gas. Now, if the volume is increasing, this is going to come out to be a positive number because V final will be bigger than V initial. So we want to call this the work done by the gas. Now, even if this comes out negative, it's still the work done by the gas. It's just that the work that's done by the gas would be a negative number. You could also write another equation. This is another equation that's always true. You could say the work done on the gas is always the negative of P, delta V. In many cases, though, maybe the simplest thing to do is just figure out the magnitude of the work, and then you can figure out the sign on your own by common sense. Now, another key concept is the heat. What's our symbol for heat?
It's Q.
Right. Now, there's also a way to figure out the heat that's exchanged in this process, and this is one of the equations I didn't have time to go over in the other video series. So here's the equation that we would use for the heat that's being exchanged here. So this stands lowercase n, C with a subscript p, and then delta T. This is the subscript p. What do you think the lowercase n stands for?
I think we talked about this last week.
That's right, the same thing as we mentioned last time.
So I think it was the number of, either the number of moles or the number of molecules, I can't remember.
The first thing you said, that's right. Last time we discussed how capital N would be the number of molecules.
Okay.
That's not used as often as lowercase n, which is the number of moles. Why don't we use this more? Because usually the number of molecules is huge. It's like 10 to the 25th or 10 to the 24th or something. That's very unwieldy. That's the whole point of introducing the concept of a mole, that it gives us a smaller number to work with.
Okay.
Now, last time that we met, we actually talked about a different way of calculating heat when temperature is changing. Now, the formula that we talked about for calculating the heat was this formula. Now, these are very similar to each other. In fact, they're so similar that both of these C's are called the specific heat. They're just different types of specific heat. So we want to make sure we don't get these confused with each other. So this specific heat over here, let's remind ourselves what would be the units for this specific heat. Remember, you could figure out the units by kind of solving the formula for C here. So what would be the units for that specific heat?
I think that it is joules per kilogram Kelvin.
Right. If you solve this equation for C, this is what you would get, and you can see that it's in joules per kilogram per Kelvin. So what does the specific heat of a substance tell us about that?
I think maybe how hard it was to add or remove heat, or how much energy it took.
How hard it is
A certain
to
how
change
hard-
the temperature.
For a certain
Let's
amount.
remind ourselves of, say, liquid water.
Mhm.
Remember that liquid water has a specific heat of 4,184. Now, what specifically does that tell us about liquid water?
That it takes 4,184 joules of heat to increase the temperature of 1 kilogram of water, maybe,
To increase the temperature of 1 kilogram of water by how much?
by 1 Kelvin.
That's right. So we talked about how it's useful to imagine that there's a 1 in front of these units. Putting a 1 here doesn't change things. So what was the answer to my question? I was asking you in general, what does the specific heat tell you? It tells you how much heat it takes to raise the temperature of 1 kilogram of the substance by 1 degree Kelvin, or 1 degree Celsius. How much heat does it take to raise the temperature of 1 kilogram of a substance by 1 degree Kelvin? Now, let's figure out what this CP would tell us. Well, what would be the units for CP? Well, first of all, we have to solve this equation for CP,
So it would be,
and then we could figure out the units.
so joules per mole Kelvin.
Right. So now let's figure out what this type of specific heat tells us about a substance. Remember that this specific heat told us how much heat it would take to raise 1 kilogram by 1 degree. Well, what would this specific heat tell us?
How much heat it takes to raise 1 mole raise the temperature of 1 mole by 1 degree Kelvin.
That's right. So you can see that they're answering very similar questions. We're just focusing on a different way of measuring the amount of the substance. Obviously, the more of the substance you have, the more heat it's going to take to raise the temperature. So we have to specify how much we're looking at. Well, this type of specific heat focuses on the amount, on the mass that you have, how many kilograms that you have. Now remember that theoretically this tells us 4184 joules for 1 kilogram by 1 degree Kelvin, but we can still use this for any mass by just multiplying by m. For example, if you had 2 kilograms, it would be 2 times 4184 to figure out the amount of heat. So the specific heat tells you directly about how much heat it takes to raise the temperature of 1 kilogram, but it tells us indirectly about how much heat it would take to raise the temperature of any number of kilograms. Well, this tells us directly how much heat it would take to raise the temperature of 1 mole of the substance, but it tells us indirectly how much heat it would take to raise the temperature of any amount of the substance. You just multiply by the C by the number of moles. So the names for these, this is what's called the mass specific heat. And this is what's called the molar specific heat. Those are logical names, mass specific heat and molar specific heat. They show how they're similar and how they're different. The way that they're different is that one focuses on moles and one focuses on mass.